Welcome to a video on the derivative of a vector-valued function. We can see here that to determine the derivative of a vector-valued function, we need to determine the derivative of each component of the vector-valued function. Let's go ahead and take a look at an example, and then we'll look at this geometrically as well. So if we want to find the derivative of this vector-valued function, the first thing we need to do is rewrite the functions in terms of t in a form that we can easily apply the power rule. So we're going to go ahead and rewrite this as 5t to the negative 2 times the unit vector I minus 4t to the power of 1/2 times the unit vector j. And now we can apply the power rule to find the derivative of this vector-valued function. So we're going to have negative 10t to the negative 3 times I minus, here we'll have 1/2 times the 4, that'll give us 2, and then 1/2 minus 1, that'll be t to the negative 1/2. Let's go ahead and simplify this. We have negative 10 over t to the third, and here we're going to have negative 2, and we'll move this down to the denominator. It's going to be the square root of t times the unit vector j. Now remember, when we found derivatives before, the value of the derivative function gave us a slope at a given value of x. So if we evaluate the derivative of this vector-valued function at, let's say, t equals 1, this will give us a tangent vector to the curve at t equals 1. So the tangent vector would be negative 10I minus 2j. Before we take a look at this graphically, remember that this means the initial point of this vector would be at the origin. So this vector is in component form. But what we're going to do is actually move this vector to the point on the curve when t is equal to 1 to get a better feel for this tangent vector. So what I mean by that is this. In pink, we have the curve generated by the vector-valued function r of t. This red vector is the vector generated by the vector-valued function when t is equal to 1, and this blue vector is the tangent vector when t equals 1. Again, remember, in our example, we had it in component form, meaning it would be down here at the origin. We just moved it up to the point on the curve when t is equal to 1, and you can see now that it is a tangent vector. Let's go and take a look at another example. Notice this vector has an x, y, and z component, so we'll have to find 3 derivatives. Let's go ahead and do that. The derivative of this vector-valued function will be the derivative of cosine t times the unit vector I. Well, the derivative of cosine t would be negative sine t, so we'll have minus 3 sine t times the unit vector I plus the derivative of 2 sine t is going to be 2 cosine t times the unit vector j minus 2t times the unit vector k. Now for an illustration, let's go ahead and evaluate this derivative at t equals pi over 2. Well, the sine of pi over 2 would be equal to 1, so we'd have negative 3i plus the cosine of pi over 2 would be 0, so we'd have 0j minus 2 times pi over 2 would be pi, so we have pi times the unit vector k. Or if we wanted to, in component form, it would be negative 3, 0, negative pi. Notice this vector is in component form, but what we'll do graphically is take a look at this vector when the initial point is at the terminal point of the vector generated by the original vector-valued function at pi over 2. So again, in purple, we see the curve generated by the original vector-valued function. The red vector is the vector generated by the original vector-valued function when t is equal to pi over 2. And then in blue, we see the tangent vector at the terminal point of that red vector. Again, we found it in component form. We just move the initial point to the terminal point of the red vector to give a better illustration of actually what's happening when we evaluate the derivative of a vector-valued function at a given value of t. Let's see if we can find the derivative of this vector-valued function. So we first need to find the derivative of 3 tangent 7t. This is going to require the chain rule where u is going to be equal to 7t, which means u prime is going to be equal to 7. So the derivative of 3 tangent u is going to be 3 secant squared u, which is actually 7t, times u prime, so we have another factor of 7, plus, now here it might be helpful to think of this as sine t squared, because this will require the chain rule where sine t is actually u. So the derivative of this is going to be 2 times sine t to the first power times u prime. Well, the derivative of sine t is going to be cosine t. And then we're going to have minus 4 times the derivative of natural log t. Well, the derivative of natural log t is going to be 1 over t. Let's go ahead and clean this up. I'm going to go ahead and write this in component form to save some space. So we're going to have 3 times 7, that's 21 secant squared 7t for the x component. The y component is going to be 2 sine t cosine t. And the z component is going to be negative 4 over t. I think we'll go ahead and stop here. I hope you found these examples helpful.